We shall discuss now a very important topic, that is of insolation with reference to Earth. We have discussed about insolation and the spectral irradiance of the Sun in a generic manner, where the Sun's spectrum does not change and the insolation of the Sun's spectrum remains unchanged in whichever direction that you look at. However, for a person on the Earth or a person with reference to the Earth, the insolation is not constant. On Earth, during night time, there is no solar radiation and therefore the insolation is zero. During noon, the solar radiation is maximum and therefore the insolation is maximum. During morning, dawn, and during evening, dusk, you will see insolation at a very low value. All this is because the Earth is rotating about its own axis. These are the diurnal changes, and the Earth is also revolving about the Sun in an elliptic orbit, giving rise to seasonal changes, and all these affect the insolation at a given locality on the Earth. Therefore, it is very important that we study insolation due to the Sun or due to the Sun spectrum with reference to the Earth. So how do we correlate this Sun spectrum and arrive at insolation with reference to the Earth is very important for sizing the solar PV panels, and that would be the focus of the discussion now. I would like to revisit the solar spectrum once again. So here you have the spectral irradiance and the insolation in kilowatt per meter square. This picture, this graph, is with respect to the Sun's spectrum. It is independent of time. However, for a person situated at a point on the surface of the Earth, the insolation would vary with time. So the time of day is an important parameter that needs to be considered. For example, if it is at night, the insolation value would be 0 and it would be at a maximum value probably at noon. So the insolation value would probably be at a pretty low value at around 6 o'clock in the morning and gradually increase to a peak at noon and then further decrease again to 0 by dusk. So how does one visualize this insolation with respect to time also? So let me introduce here in this graph a third dimension, which is the time dimension, and let us see how the insolation plot looks like. Here I have recomposed the insolation graph. Instead of the plot function, I have used the mesh function and plotted the insolation using time as a parameter. So you see here a family of curve. The x-axis of course is the wavelength and the y-axis is the insolation in kilowatt per meter square. This bottom line is at a pretty low insolation, which probably may be morning near 6 o'clock, 7 o'clock, and then as the time increases in the day, you will see the insolation rising and rising further on as the time moves towards noon, and probably at noon it may be at the max of the peak value, and then further on it would again fall down and coming down to 0. So as I have used the mesh 3D, I should be able to rotate it and just get a much better view of how it would look. So this now this position gives you a much better idea of what is happening. You see that the time axis is going down into the plane of the screen. So this is the time in day, time in hours, 0 to probably 24, somewhere here. This as usual is the wavelength, and this as usual is the insolation kilowatt per meter square. And you see that if I start here from 0, which is 0 hours midnight, and this is at 5 o'clock, and probably at around 6 a.m. it starts to rise the insolation value, and the insolation value would probably peak at around somewhere here noon, 12 o'clock, and then 13, 14, 15, so on, it comes down, and probably at 18, which is 6 p.m. it again goes down to 0, and then remains further 0 during the night. Of course, this this profile will change depending upon the latitude. At the equator it will be different, at the northern latitudes it will be different, at the southern latitudes it will be different. But at a given longitude, latitude point, at a given locale, you will have a profile something like this over the day. So every day this profile will repeat. So this is the important takeaway that I would like to give you for the insolation at a point on the Earth. I am assuming right now there are no atmospheric conditions, but we will discuss that later. But for now, important thing that you should understand is, for a person standing on the surface of the Earth at that locality, the insolation is highly dependent on the time of the day, and this is the diurnal changes, and this happens every day because of the day-night effect, because the Earth is rotating on its own axis. I shall include for you also the script file which generates this. I have made that in insolation_3D, and I will include that also in the resource that I would place for you, the resource section. Once we know the daily insolation profile, we will be able to derive the solar photovoltaic panel requirement in terms of peak power. So let us put the insolation profile with respect to time that we just now saw on this screen. So we have the x-axis, which is the time axis, and the y-axis, which is the insolation in kilowatt per meter square, and we saw that this is the kind of profile that we get. Peak, I have put it at around noon, not necessary that it should be at noon. Now, if you take the region within this green insolation profile and take the area within this region, it is nothing but the energy, because it is the kilowatt per meter square into the time in hours will give you the energy in kilowatt hours per meter square, and let me denote that by uppercase H. So if we make measurements, let us say if we make either measurements or estimation at a particular latitude, we will get this curve, and the area under the curve should give us the energy per meter square per day for that particular local latitude. Now, this area can be approximated or can be represented equivalently in terms of the standard insolation. So if we consider the standard insolation line, it is in this fashion. So this is a 1 kilowatt per meter square line, and this is the standard insolation line. Now, using the standard insolation line as the upper limit, we can draw a rectangle like this, such that the area within the rectangle is matching the area H of the actual measurement or estimation. So this width of the rectangle is, let us say, H hours. Then what is the area of this rectangle? This is 1 kilowatt per meter square height into H hours. So this will give you H kilowatt hours per meter square per day. Now this is the energy that is contained within this rectangle, and if we make this energy equivalent to the energy, the actual estimated energy at that place, which is H, then we would know what is the equivalent hours of standard insolation time. So if this energy is made equivalent to the actual energy of that place, then the H hours of standard insolation time is equal to H kilowatt hours per meter square per day. And this insolation can be used to derive the peak power requirement of the PV panel. Now let us say that WH load is the required energy, and WH load by H is the peak power requirement for the PV panel. So WH load is again energy in kilowatt hours, and if let us say this WH load is the required energy, daily energy for that day. Now that would mean that the requirement is filling up this has to fill up this rectangle. Now I know this H has been obtained. If I am able to estimate H, the uppercase H, in kilowatt hours per meter square per day, then that will directly give you the value of how many hours in a day with standard insolation. Using that here, you will get the peak wattage required. Now that would form the basis for you to select a PV panel with this peak power requirements. Now with data sheets and series parallel connection, you can choose the number of panels that are needed for series connections and parallel connections. So in this way you can arrive at the size of the panel. But the difficulty here is how to get this H, because this H has many uncertainties. The uncertainties are, as I said, the daily, the seasonal, the water vapor content in the atmosphere, the clouds, the weather conditions, climate conditions. All these are going to affect this H, that is the incident energy falling at that particular locality or particular latitude. So if we are able to get this with reasonable accuracy, then you would be able to size the panel appropriately. So our whole focus is to see that we get this kilowatt hours per meter square per day, that is the energy per meter square per day, as accurately as possible. Estimation of the incident solar energy H in kilowatt hour per meter square per day is an important activity that we have to now take up if we have to appropriately size and rate the solar PV panel for any given application. However, this incident solar energy is dependent on many factors and many parameters. So it is important that we have a look at these factors that affect the solar incident solar energy H. A note of caution, this H I am calling as the incident solar energy in kilowatt hours per meter square per day. In literature, you will find the solar energy is also referred to as irradiance, as solar irradiance. We have used the term spectral irradiance. So distinguish spectral irradiance and solar irradiance. The units are different. Spectral irradiance has the units of kilowatt power per meter square per nanometer. Solar energy or the solar irradiance has the unit kilowatt hour energy per meter square per day. So keep this distinction in mind. But as far as my discussions here, I will not be using the term irradiance for this. I will just use incident solar energy so that it reflects closely to the units of the energy that we keep writing for H. So be cautious about this particular variable. It is also called solar irradiance in the literature, but note the units. One of the important obvious factors that affect the incident energy is the geographic location. So the geographic location is represented by two parameters, two variables. One is phi, latitude represents the latitude, and the other is lambda representing the longitude at a given place. Another factor that affects significantly this value of H is the collector orientation. By collector, I mean here the solar PV panels. Solar PV panels are always flat. They are flat collectors. However, in the thermal applications, the collectors need not be flat. You will see parabolic and cylindrical paraboloids being used as collectors, and they have different concentration profiles. However, for the solar photovoltaic applications, the collectors are always flat, and I am always meaning the flat plate collectors and the orientation of the flat plate collectors to the horizon plane or the horizontal plane. So that is the angle which we understand here by collector orientation, and that angle is denoted by the symbol beta. So this is also called the collector tilt, the tilt angle. Another very important factor is the time of day. This is something that we have discussed already, and we saw how the insolation is affected by the time of the day, and we use the symbol omega for hour angle. Omega, the hour angle, represents the time of the day, and which also represents the diurnal changes and diurnal effects. Another effect is time of year. This is another factor which seriously affects the value of the incident solar energy. We represent this by symbol delta, and it is called declination. I will explain later what declination is, but this is an important parameter. This actually represents the seasonal variations and the seasonal effects on the incident solar energy. All these parameters which I have listed are fairly deterministic. However, the one that I am going to now say, which is the atmospheric effects, is the one which is most difficult to estimate. The atmospheric conditions like cloud conditions, water vapor content in the atmosphere, gases present in the atmosphere, etc. All these things affect the incident solar energy. Now, all these are not deterministic. On a given day, we don't know what is the condition and what is the effects. You have to take probably the statistical values for all these. This is represented by a variable called kt, and it is called clearness index. And this probably is the most difficult to estimate due to the uncertainties in the atmospheric conditions. So we will look at all these parameters and variables and see how we go about obtaining these parameters, and then once we have these parameters, how it gets integrated into the estimate equation for H.